Hi friends, in this video lecture we'll try to understand second law of thermodynamics. Well, to begin with, second law of thermodynamics is a law of nature, unarguably one of the most valuable findings of mankind. But this law is somewhat confusing for most of the engineers or for most of the students. Confusing mainly because it has got many statements and there are terms like entropy, Gibbs free energy, etc. etc. And purpose of this lecture is to remove these confusions and give a physical insight about second law of thermodynamics so that you can apply it in your engineering field or even in your daily life. Along with that, we'll understand meaning of entropy and Gibbs free energy. Okay, so let's go into it. So the $1,000,000 question, this law is used for what purpose exactly? Well, there are many uses for second law of thermodynamics, but one of the most important uses is to determine whether a process is spontaneous or not. Or in simple words, whether a process will happen by its own or not. Let's consider a few examples. Here two gases are mixing together and air is getting leaked from a tank and a mass is falling down. A hot tea is losing its heat. So you can see in all these processes from state 1 to state 2, the process will happen spontaneously, means without any external aid. You can see the gases will mix together spontaneously, the air will get leaked spontaneously. And what about the opposite reaction, the reverse process? Will it happen spontaneously? Will the mixed gas become unmixed spontaneously without any external force? That will not happen, right? From your experience, you know that that process is impossible, that is not spontaneous. But according to energy conservation or first law of thermodynamics, even the reverse process is possible because in both the states energy is conserved. So what is missing here? There must be one more law which will govern direction of a process, which will predict direction of a process. And that law is second law of thermodynamics. So if you apply second law of thermodynamics for all this process, you could see in which direction a process can happen. Now obviously there must be a question in your mind. Do I really require a law for this? Just to predict direction of a process? I can predict direction of all this process by intuition. And if you have such questions in your mind, that is natural. So we will analyze one more example. Here it is, a chemical reaction. Here I am putting two chemicals together in a chamber and I am waiting for a reaction and I am checking whether this reaction will happen, where one atom of blue chemicals react with two atoms of green chemical and forms a new molecule. So I want to check whether this process is spontaneous. So do you have answer for this from your intuition or from your experience? Not straightforward, right? When the process was simple, you are able to predict direction of the process. But when the process is somewhat complicated like this, you are not able to predict. And this is exactly where second law is used for. To predict direction of a process, even for a complicated process. So in this lecture what we will do, we will go across second law, we will learn it well and we will come back to the same problem, to this chemical reaction. And we will see how second law can help to predict direction of the process. So let's get into it. In this section we will see what is second law of thermodynamics. Well, if you check some standard thermodynamics textbook, you could find mainly two statements for second law. One is Cauchy's statement, second is Kelvin-Planck statement. And about Cauchy's statement, consider this system where you have got a cold body and a hot body and heat is flowing from cold body to hot body. Assume this is the only process happening, this heat flow. And according to Cauchy's statement, this process is impossible. That is Cauchy's statement. And about Kelvin-Planck statement, consider this system where you have got a heat reservoir or a heat source. This is an engine. And this engine is absorbing some heat and is producing equal amount of work, means it is not wasting any amount of heat. And according to Kelvin-Planck statement, this engine is impossible. That's it. Well, these two are two classical definitions of second law. They are true, they are similar, but problem with these laws are they are not in a form which is directly useful for engineers. So in our study we will use one more statement of second law, which is again derived from Kelvin-Planck statement. That is Cauchy's inequality, or in simple words, Cauchy's inequality is second law of thermodynamics again, which is useful for engineers. And let's see what it is. Here it is. This small equation is known as Cauchy's inequality. A small equation, but it has got a deep physical meaning. We will analyze this. You can see this is a cyclic integral. So you are integrating some quantity over a cyclic process, and here I have put B. B denotes boundary of the cycle. So you are integrating some quantity along boundary of a cyclic process. And what is that quantity? Quantity is dq by T. dq is heat absorbed at the boundary of the cycle, and T is temperature at the boundary of the cycle. Please note that this temperature should be in absolute or in Kelvin. And if you do such an integration, Closures inequality states that this value will be always less than or equal to 0. That is second law of thermodynamics. And if you are confused about this equation, we will try to work out a problem so that you will get some physical insight about this. Here it is, a very simplified power plant cycle. And I have drawn boundary of the cycle here with the dotted line. And the only heat interactions happening here are heat absorption at the boiler and heat rejection at the condenser. In order to simplify our analysis, you are again assuming that both condenser and boiler are at uniform temperature. So you can easily apply Closures inequality to the system, and LHS will be like this: QB by TB minus QC by TC. Here sign is negative because heat is getting out of the system. Please note that use of integration is not required here because both the boundary were at uniform temperature. And according to Closures inequality, this quantity should be less than or equal to 0. Here it is. This is second law of thermodynamics for this system. Now I am applying a small trick to this equation. I am making this inequality equation to an equality equation like this. I am introducing a new term called S production. And significance of this S production is degree of irreversibility. Irreversibility means effect of friction, turbulence, or vortices which is present in a system that will make permanent energy loss to the cycle. In an actual system, irreversibility will always be there, so the S production quantity will be always positive. And if you can assume that if my system is perfect, there is no friction, there is no turbulence, then you could put value of S production as 0. The equation will be simplified like this. And interesting thing is that if irreversibility is within this cycle is 0 or S production is 0, then this cycle will give maximum possible thermal efficiency. This is another use of second law, where you could analyze any cycle, whether it's refrigeration, whether it's Brayton, and you can assume that heat interaction happening at uniform temperature, and when irreversibility is in those cycles are 0, this cycle will give maximum possible thermal efficiency. So this is second law for a cyclic process, but most of the time you have to apply second law even if your process is not cyclic in nature. So in next section we will see that how to apply second law thermodynamics for a process which is not cyclic in nature. Second law for a process. Assume you have a process 1 to 2, and assume it doesn't have any irreversibility. It is completely reversible. Then using Closures inequality I can prove that the LHS of Closures inequality is a constant quantity. Means it doesn't depend upon path of integration. It only depends upon the end states 1 and 2. Since this integration doesn't depend upon path of the process, you could express this integration as a difference of property. And you know, definition of property is that it doesn't depend upon path of process. And you will call this property as entropy, the famous entropy. Integration 1 to 2 for a reversible process will represent like S2 minus S1, where S denotes entropy. So please remember, entropy is property only if the process is completely reversible. So this is second law definition for a process which is reversible. What if the process is not reversible? It will be like this. Entropy difference will be sum of two quantities. First is same as heat transfer entropy generation. Second is entropy production. And we already saw entropy production in previous slide. This one arises due to effect of irreversibilities. First quantity will be known as entropy transfer term. Second will be known as entropy production term. And one thing to notice here is that the value of entropy transfer term and total entropy change term can be either positive or negative. It can be anything. But entropy production term will be always positive. This is second law for an irreversible process. In this section we will derive a very useful form of second law which can be applied to any process. Assume you have a system here and it is releasing some heat to the atmosphere. So there will be entropy transferred to the surrounding and it will also lose some entropy. Now let's analyze this system in a different way. Like this. You are analyzing the system and surroundings together. Means you are analyzing the universe as a whole. So you know across universe there won't be any heat transfer because you are taking the complete universe. And within universe there will be heat transfer, but that doesn't come in closures inequality part because we are only concerned about heat transfer at the boundary. So the equation we derived in last section will be simplified like this. The entropy transfer part is 0. So you could say entropy change of universe is same as entropy production. And we said already that entropy production is always positive, or entropy of the universe always increases during a process. This is increase of entropy principle. Means if I sum entropy change of the system plus entropy change of the surrounding, it will be always positive. So this is the most simplified and straightforward definition of a second law for a process. Now we'll use this increase of entropy principle and we'll try to work out two interesting problems. Let's see it. So the first one, the famous hot tea problem. So the basic question is, will this hot tea absorb heat or release heat? First assume that it is absorbing heat. Assume, let's say it is absorbing 10 joule of heat. And what I'm going to do here, I'm going to calculate entropy change of universe. And you know entropy change of universe is entropy change of system plus entropy change of surrounding. Since this hot tea is absorbing 10 joule of heat, the entropy change of system or entropy change of hot tea is 10 by temperature of hot tea in Kelvin. And the same amount is lost from the atmosphere or from the surrounding. So entropy change of surrounding is minus 10 by temperature of surrounding. And if you add this to quantity, you will get entropy change of universe as a negative quantity. This is not possible. This is again a second law or increase of entropy principle. Now let's say it is releasing some heat. So Q will be minus 10 in this case. In that case, you can find entropy change of universe as a positive quantity. So this is feasible. So using increase of entropy principle or second law of thermodynamics, we proved that the hot tea can only release heat. It cannot absorb heat. Now the second problem. The same problem we tried to solve in beginning of the lecture. Assume the reaction has happened and entropy system has increased by delta S system. Also it has gained some enthalpy, which is same as heat gain of delta H. Now what I have to calculate? Entropy change of universe. And you already know entropy change of system here. And what will be the value of entropy change of the surrounding? And here is a clue for that. You know heat absorbed by the system. So same amount of heat is lost by the surrounding. So you can say entropy change of surrounding is minus delta H by T. So entropy change of universe is sum of these two quantity, system plus surrounding. So if this quantity is greater than 0, then this process will be feasible. Now let's try to rearrange this equation. Since temperature T is always positive, if I multiply this by minus T, then inequality equation will become like this. When delta H minus T delta S less than or is equal to 0, this process is possible. And you can denote left hand side of this equation as something called Gibbs free energy. Or in simple words, when change of Gibbs free energy of a system is less than or equal to 0, that process is possible. This is the advantage of using Gibbs free energy. Unlike an increase of entropy principle, here you need not to worry about what is happening at surrounding. You can concentrate your study only on the system, and you can predict whether a process will be spontaneous or not. So this is all about second law thermodynamics. So as conclusion, second law determines direction of the process. It determines maximum possible performance of a cycle. And if a process is spontaneous, in either of this case, both are in fact same when entropy change of universe is greater than 0 or Gibbs free energy change of system is less than 0. Thank you for watching the video. Have a nice day.